Good evening and welcome to the live sessions. It is 6 p.m. but participants are yet to join. So we will wait for a few more minutes before we get started for today. Thank you. Hello everyone, and good evening, and welcome to the live session for the course on fundamentals of additive manufacturing technologies. This is week 3 of the live sessions, and till now we have been introduced to additive manufacturing, its various classifications, and we have also been studying about some computer-aided process planning steps. For instance, previously we have discussed in depth about support structures, when they might be needed, how to generate support structures from the sliced configuration, what is slicing, what are the different types of slicing, and particularly last week we spent quite a lot of time discussing about support structures themselves. So this week I wanted to show a few videos. Just allow me a minute to share my screen and then we'll discuss further. Yeah, it's visible now. So this first is a video by Wilson. Some of you who might be playing basketball or tennis might be aware of Wilson, the company, which is a big player and is famous for making rackets, balls, and a basketball in this case. Except the basketball is 3D printed. So let us take a look at this video. So as you saw, it's a 3D printed basketball. I am not sure about the material, but it had a lattice-like structure, so it is hollow and made up of some intricate shape all throughout. The interesting thing is that it has been designed to bounce and behave just like a regular basketball. I am sure its weight is also very carefully chosen so that it resembles the feel and say functionality of a regular basketball and bounces accordingly. I'll just play the video again. This shows us that additive is not really limited to printing cubes or just some very simple prints using FDM type machines, which we might have seen in our labs, maker spaces, or somebody even might have them at home. The second video, though, is far more interesting from a research perspective. We spent a uh, major portion of the last week going over support structures and the need for them. But here, let's see the video first. I'll play it again just to drive home the message. We printed a structure seemingly in thin air, and it's a horizontal structure without the use of any supports, which really makes you think if supports are really needed as much as I've been emphasizing all of last week, and what possible technological invention could have made such writing in thin air possible. One hint which you can take is the glow, the blue glow, which is actually following this most recently deposited material, and maybe that can help you guess about the nature of this printing process. For those of you who might be interested further, this video is from Vivolver, so you may visit their website or other web resources to find out more. For now, we'll return to our regular sessions. Okay, so once again, I welcome you to this live session for the course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajin Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This is the last lecture on the module for tool path planning, and the contents mostly deal with area filling methods such as grid cutting, pixelation of a surface, the use of masks, then various tool path strategies such as rastering, directional, bidirectional, contours based, spiral, medial axis transformation, and others. The reason why we are stressing on area filling methods is, I mean, some of you who might have worked or might be working in additive manufacturing know that the typical way to fill a contour again, I would remind you, is the intersection of a slice with the exactly sliced or approximated sliced object, and the contour in each layer which is to be deposited will have say 2 or 3 perimeter layers, and the rest of it, the infill region, is filled using these area filling methods. Again, we are well aware that the characteristics or the properties of any such deposited part uh, on the surface will be different from the bulk behavior, and we are actually interested in the bulk behavior for the reason that it decides the final material properties and so on. The surface is expected to be different. So we study area filling methods here. And it was mentioned that there are two main steps to convert any 3D CAD model uh, into the control data for an additive machine: slicing and toolpath planning. Toolpath planning being a critical step because it is reported to influence surface roughness, dimensional accuracy, and path strength of the printed parts. And the major components for a toolpath are the outer boundary and the inner boundary. These are what I was referring to as the perimeters, so to say, and the area filling path. Again, the considerations for area filling of the support are different because, as we have been discussing, the supports are of a sacrificial nature. They are not actually part of the final build structure, and we want to get rid of them later. They only serve the purpose of supporting any overhanging features. However, they are not a feature themselves. And since we want to get rid of them later, we inherently make them weaker or easier to remove, or say prone to some form of chemical attack, so that it is easy for us to get rid of them. Thus, because of these considerations, the area filling strategies for the support structure is also different compared to the inbuilt infill of the bulk material. For instance, we can have a lower density or a lower infill ratio for the support structures. Typically, when you would want, say, close to 100% density in the actual build of the material, often the density of the support structure is kept close to 40%, for instance. And most of the area filling methods, which we'll be discussing, are for 2D surfaces. They can be expanded to surfaces in 3D or freeform surfaces, but the working principle remains much the same, and they consist of grid cutting, pixelation, the use of masks, and filling paths. Uh, it is important to take a minute to discuss the reason for choosing an optimal or well-planned area filling method, because given surface, you are free to fill it any way you like, just like we would color shapes with crayons. It does not really matter whether you first make an outline and then fill the insides, or start at the inside and move outwards, or whether you go horizontally side to side or vertically up and down, because what you want to do is at the end of the day fill it. But what are some of the engineering considerations which drive our decision into choosing a particular strategy for it? First is the need for quick heat dissipation, and people who are working in additive might already be aware of it. In most AM processes, the material will be added through some form of melting of the raw material and deposition on the surface. For instance, the process which I work with, laser DED, involves the melting of the powder or wire feedstock, also some extent of melting of the solid substrate itself, and then deposition of the molten droplet from powder or wire into the molten substrate to form the part. Now, when I say molten, it clearly implies that we are uh, above the liquidus temperature for the alloys that we are working with, and often we'll have a certain degree of superheat. In the region of highest temperature concentration, it can even go up to 2500, 3000 Kelvin. These are not uncommon numbers. Now, as such, because of such high temperatures, it is expected that the workpiece and the substrate will heat up and then warp due to thermal expansion. What is warping? We might be aware, but it's always a good idea to revisit. Typically, when we plan our 3D printing process, say for the simple example of a cuboidal tower, this is our substrate. Typically, say a flat plate of a certain minimum thickness. For the machines we use here, it's typically specified as 1 inch or 25 mm. The idea being that it should be thick enough so that it does not warp easily. But what is warping? And say we just slice it using some uniform slicing, planar slicing method. Now, because of the high temperatures and the heat fluxes involved here, typically we would say clamp it to the build plate, to the machine bed using some, say, bolts, or even C clamps. So, but still what happens is, and what we notice later is that typically the substrate plate tends to warp upwards. And now we can clearly see that previously for my deposit, whereas I had a flat substrate plate, and all my calculations and design considerations and toolpath is built in according to that, in accordance with that. Now, the deposition area is curved, and so should your deposition head move in a plane, it is very likely to hit this plate. Also, the build quality which you will get will not be the same as a part built using a flat substrate. Again, another type of warping which may be encountered in certain cases is when your plate is actually curved upwards, in which case your head will definitely collide because we had started with the reference plane uh, far below where we are right now. And so it is important to prevent warping. Warping typically happens because of differential thermal expansion and the accumulation of heat. Further, this is all about warping of the plate, but what about warping of the part itself? So we take a lot of pride in saying that additive manufacturing helps us in printing near net shape parts.
Excuse me.
Hello, Ramamurthy. Yeah, you had a question.
So in that above earlier example, so
Yes.
what is the material with which that substrate is made of?
Typically, I can give you an example from my own research. Typically, the substrate material and the build material will be compatible. So, say for build materials which are stainless steel, say 304 or 316, or some nickel-based superalloys like 718, 625, or even titanium 64. The
Okay.
substrate in all these cases is just SS304 or 316 plate.
So all are metal additive manufacturing only. Okay.
Yeah, the examples which I am giving you are from metal additive manufacturing, but if others are working with, say, polymer or others, the case might be different. However, for metal additive manufacturing, typically it is ensured that the substrate and the build material have good metallurgical compatibility and similar, if not the exact type of thermomechanical properties as well. The reason being to avoid warping.
Okay. So, the case is, in the case of polymers, I think the situation may not be this much worst.
Correct, because in polymers anyway, the maximum temperature which we're achieving is say a couple of hundred of degrees, like 200 or 300 degrees Celsius,
Maximum.
maximum. Yeah, and the build plate is still mostly metallic, so the case is not so exaggerated in those cases. Correct.
Thank
Yeah.
you.
Still, because of the considerations of distortion and warping of both the part and the build plate, we should ensure that the area filling strategy allows for quick dissipation of heat. Second is to minimize the number of lifts, and a lift is basically motion by the deposition head, where it is just moving from one position to another without depositing. Typically, during such a process, the deposition head might also be programmed to just lift a little from the surface and not really move at the same height for the fear that what if it encounters some previously deposited feature and there is a collision. However, since because during such a lift motion, no material will be deposited, it is not really say productive time, or it does not really count towards productivity. So we should minimize the number of such lifts. A second consideration is that during the start and stop of material deposition, the process is unstable because of inertia effects. Because of this instability, there will be either under deposition or over deposition beyond the designed deposition rate. And so your part characteristics will get affected. Again, we often design our print strategy such that the material addition is at some fixed energy deposition rate. And that energy density or energy rate is a function of the build volume and the input power. The build volume again is decided by the amount of material that you are feeding per unit time. Again, say if you have kept your laser power constant, but you are feeding a larger amount of material, the temperature to which the material will rise will change because now the same amount of energy is being dissipated or distributed in a larger volume of material. All of these fluctuations can change the energy deposition rate and the material deposition rate, which in turn will affect the material properties. We want our material properties to be homogeneous and isotropic to the extent possible, or at least within the expected range of deviation from the reported values. But if there is a large change in material addition rate or energy density rates, the behavior of the part can be unexpected and can lead to premature failure. Of course, because of say the various errors or time lags involved in material addition, like at what rate your roller will be feeding the material. If it suddenly encounters some resistance, will there be a local change in the amount of material being fed? Or depending on the quality of your optics, or say your laser can be a pulse type instead of a continuous laser type. There will be some local fluctuations, but they will be averaged out. Another is the step over value. Again, to ensure uniform density and isotropic material properties, we should ensure that the step over value, which is the say, which dictates the amount of overlap between two printed layers in plane. So if this is your first pass and this is the amount of material printed, then your second pass typically will have some overlap with the first. It will be very rare that we are printing material exactly from edge to edge. And the reason again is to avoid the formation of interlayer voids. Now, there is some research, actually a good amount of research, into what is the value of an optimal overlap. What happens if we increase this overlap or decrease this overlap, and how it affects the overall material properties. And a good number is typically 30 to 40% of overlap. But again, this overlap should be constant for a print. Okay, let us quickly discuss some of the area filling methods, starting with grid cutting. And this is especially relevant to laminated object manufacturing, where the raw material is in the form of some lamina or sheet. As we discussed in our first lecture, in this case, the successive sheets of material are joined by using some form of adhesive, whether it is a thermally activated adhesive or it can be a pressure activated adhesive. And a cutting process is used to separate the region associated with part and the say unused or region to be separated. The way it is processed is at first there will be say depending on if your material is some ceramic sheet or glass. Sorry, not glass is a bad example. Say some form of ceramic sheet or metallic sheet. Then it will be laser, or if it is something as simple as paper, in which case a simple just mechanical knife will suffice. Using that cutting tool, being a laser or a knife, we scan this exterior contour, which I'm highlighting in red, and the interior contour. Next, and this is done very precisely. So if you're doing it with a laser, you will say use a very fine spot size and a controlled speed for doing this. Next, all of this material, which I am hatching right now, will go away with the sheet or is not really required as it does not form part of the build. So what will happen is we will cut it using some coarse motions, as in using say a larger spot size or a higher speed, because now we are not really concerned too much with precision. We have already earmarked the region which is important for us. Same for this inside region, which is not going to be used, and divide it into grids. The reason for this grid cutting will be even more obvious when we discuss laminated object manufacturing, where we'll actually see an example of a part which is built by this process and how later it is very easy to get rid of this excess material using such a grid cutting approach. The next method is pixelation or division of the uh, area of region interest and the remaining region into discrete pixels. Pixels, as we know, are the smallest unit into which we divide things like images, and it is especially relevant in digital light processing based WAT photopolymerization process. And just write that here. So DLP stands for digital light processing, and some other methods, some other AM processes like binder jetting and material jetting. The reason being that in these processes, whether it is light being projected or some kind of liquid binder material being injected or some material being injected, it always happens at discrete locations or discrete nozzles. If this is the bottom view of your deposition nozzle, what you'll notice is there are several tiny nozzles. Say, typically they will have dimensions in micrometers. And they can be so closely spaced together that we cannot make them apart with naked eyes. And what you will do is in a layer, say if this head is scanning somewhere here, we will only deposit material in these red regions, and for all of these other black regions, the nozzles which are placed here will not be activated. Depending on the distribution and size of your nozzles, your resolution will be higher or lower, and that's what pixelation is all about. Since this material deposition is happening at discrete spots, the accuracy at curved features will vary. If you have a very high resolution or a very small pixel size for your process and machine, you will be able to approximate these curves better. And if your pixel size is very large, then the approximation may be poorer, more erroneous. The bottom line being that the material curing or addition accuracy is governed by the resolution of the pixels. An idea which is very similar to dots per inch or DPI, which is used in 2D printing. Typically, you will notice that when you're printing or when you're saving an image, you have an option to specify the DPI. If you, or even while scanning, if you choose a DPI is something like 60 or 100, then you'll find that the image resolution is not very good. If you try to enlarge it a lot, the pixels will seem to break. However, if you scan at 300 or 600 DPI, the image quality is very good. Again, the file size will be larger. However, these were still methods where we were say even either dispersing the material at discrete points or the source of illumination was in the form of some discrete laser. But what if we are illuminating the entire surface at once? In that case, we use a mask. And the principle here is very similar to photolithography, which some of us might have studied in an earlier course of engineering. Now, in some WAT photopolymerization based processes, the entire layer, the entire layer is cured in one go by passing light through a mask. This light is typically available in the form of some floodlight-like arrangement, which will illuminate the entire deposition bed in one go. This mask can be created instantaneously using the information obtained for the slicing data, or in some cases, this mask for standardized prints, this mask may be available beforehand. As in, we have already designed and made the mask for each layer, and then we are just successfully using them for depending on the layer which is encountered. The area filling process here is created by creating a negative of the slice. And now we come to the filling methods themselves. The most common one which we may have encountered is something called the raster method, where we just start from a position, say point 1, go in a linear fashion to some point 2. Here in this case, it is aligned along the x-axis. Then this red path that you see is actually left. No deposition occurs during this path. Go back to some starting position 3 and then scan in a linear fashion till 4 and continue till this entire contour is filled. It can also be done in a direction which is along some other direction, like parallel to y-axis, or even at some intermediate angle. It need not be aligned, or it can happen along both directions for more efficient filling of the surface. The drawback in this case, which we can very clearly see, is that a large part of and a good amount of time is devoted to moving from one point to another, during which no deposition occurs. Typically, this will be a rapid motion of the CNC head. And while visualizing G codes, we might also have seen that the visualization for an actual deposition path, such as going from 1 to 2, and the visualization for a path going from 2 to 3 is different. And that is because of this lift in between. To overcome the drawback of this long lift period in the simple raster type scanning, the zigzag method came up, and it connects separate parallel lines into a single continuous pass, leading to less build time with fewer transition motions. What we do in this case is, instead of we go from 1 to 2 as before, but instead of traveling all the way back here, we go to some neighborhood point lying along the contour and continue scanning in a continuous fashion, and so on. However, the error which you can clearly foresee here is that now we are even approximating this curved edge with a straight line motion. In this example, going from point 4 to 5, or from point 1 to 4. The original curvature might have been in a curved fashion, or might have some finite value, but we are just approximating it as a linear path. Some part of it will be taken care of by the perimeter, or the say exterior contour which we have printed before, but there is still a chance that there can be some voids in this region. Thus, it's a discretization error on the edges, and the outline is poor, leading to poor surface quality of the printed part, also known as direction parallel to path. It is very commonly used in AM processes, and it consists of segments which correspond to backward and forward motion in particular direction. Now the other paths which have been proposed and put to use are this contour path, which is a biomimetic concept. And here what we are doing is we are simply offsetting this outer contour of the shape inwards by some fixed distance. The gap between these contours remains uniform. So the contour path creates a series of offsets starting at the outer boundary and progressing towards the center. It is a biomimetic concept because if you have ever looked at the cross section of a cut tree, what you will notice is there are these rings in the tree, which show the growth of trees. And there's also some trend by which you can identify the northern direction or the magnetic poles of the earth. And they have been used to estimate the age of, say, old fossilized trees and so on. or years in which ample nutrients were available or there was some climate change. In this case, the contours start at the center and move radially outwards. In our case, however, we first print the outer perimeter, then we keep offsetting this contour inwards as we move towards the center. All the closed loop contours in a sliced plane are collected together in a pattern to be offset, and the toolpath has to be restricted in the area defined by the boundaries of a cross section. Some other names used to refer to it are contour parallel path or model offset path, and so on. A drawback of this elegant method is obvious for this complex shape here, where we see that the contour has been offset, but there are uh, seemingly voids in these regions where the local density of material is very low. While away from the center, the deposition of material appears to be constant. Another example which has been put forth is the spiral toolpath strategy, which may be commonly used in subtractive machining or numerically controlled machining, as it says here, but it is not encountered very frequently in additive manufacturing. And that may be so because it is suitable only for a very few specific geometrics. Uh, as one can visualize, if one uses such a spiral toolpath to move inwards towards the center, it can lead to the accumulation of heat because now you're not allowing a lot of area for that heat to dissipate. Then there are these new methods such as space filling paths, where instead of just moving along some straight line or simple curve, we use these space filling curves. Some examples of which are the Hilbert curve, piano curve, E curve, and so on, to fill cross sections in a layer. Here, for a chosen shape of a given size, the offset is always uniform, as well as there is a very small number of liftoffs, and the deposition process is almost continuous. As in, you can actually start from one point, say here, and you will only lift your deposition head after reaching the other end, after depositing the entire shape, which leads to time saving. Another method is MAT, or medial axis transformation, because as we discussed, some of the other methods do not really cover the geometries of parts, complicated parts, and may leave voids or gaps. We take another concept from nature, which is the concept of skeleton. Say if you have a complex shape here, we between any two boundary segments, we construct a circle, which is to which these boundary segments are tangents, and we collect the center of such a circle. Here the edges have diverged, so we draw a larger circle. On the left here we have a different set of edges, and so on. We keep on collecting these centers to make this skeleton of the structure. Once we have the skeleton, we simply offset it till we reach the exterior contours. And it is especially useful for complex domains. The same shape which previously had a vulnerability to leaving voids or gaps, now we can see that the deposition in almost all regions is uniform and the local density is almost uniform throughout. Now, the most optimum one, of course, will depend on your specific use case and is expected to be a hybrid path which incorporates two or more types of paths that we studied, such as in this example, which has incorporated a combination of zigzag path and a contour path. Continuous paths may also be useful, as we were discussing. Some of those space filling curves ensure that you lift up your head only once after the deposition in the entire layer is completed. The obvious advantage being that the start and stop of material deposition are times of instability, and if we minimize the number of lifts, we can override this instability effect. The number of times the process is switched off or on in a slice should be minimized, and in this case, it can be brought down exactly to one. A continuous path can fill the entire slice area in a single continuous path from start to finish and will eliminate the air passes. Air passes being the motion of the deposition head, as I described. When you stop depositing material, lift your head some distance above the uh, previously deposited layer height and then move it from one position to another. Maybe, say, if on the same build plate you have multiple parts being printed, or you specified your toolpath so that it finishes in one place and the next loop starts from some other location, and so on. In this air pass, the head will simply be moving without depositing any material or with the laser switched off. Typically, it will be a rapid motion, but then even then it consumes time. And finally, there are some well-defined topological shapes and structures which you can use, which you can use for infill of your part. Some of the common examples are shown here, such as on the right we have this honeycomb structure, which, like most other things, again, is a nature-inspired concept and which we know is very strong in compression. Another example which we commonly encounter is this gyroid shape. And gyroids have been found to be especially useful in biomedical implants. Now, I do not work in biomedical additive manufacturing, but from what I can recall or guess, it might be because this gyroid shape prevents effects such as stress shielding, where you do not really want the implant to take more stress than a normal human bone, because then the human bone will become weak. You want the distribution of stress to be equal or in some well-designed proportion. And second, this gyroid shape may be useful for osteointegration and the development of new bone cells and bone tissues. And also, it may be resistant to, say, bacterial infection and bacterial attack. Again, I am not myself working in biomedical implants, so I cannot say this with 100% conviction, but this is my guess. And then there are these other shapes which these days come pre-built or pre-designed into any common additive manufacturing software like Simplify 3D or Ultimaker Cura, or the one which you have here is Multi Horizon. You can just use or simply select this from a drop-down menu, and the software will automatically fill your contour in each layer with this infill strategy. There are also some studies which compare how, say, a triangular strategy compares to a cross or a trihexagon or a zigzag and concentric and so on. And it has been reported that based on the type of infill strategy, the final build part can have different strengths, different ductility, or it can have varying degree of isotropic behavior. As I mentioned, we will only study the methods for 2D surfaces or surfaces or slices in a plane. The same principles can be extrapolated to 3D or free-form surfaces. However, we'll not discuss them in detail here. And now just a quick introduction to liquid additive manufacturing. As you guys would recall, ASTM has classified additive manufacturing into seven distinct process types. However, for the purpose of this course, that categorization is slightly different. The categorization here is based on the type of feedstock material being used, whether it is solid, liquid, or gas, but then no known uses of gas-based AM are available. In solid again, whether it is powder type or laser wire type and so on. We start our discussion with liquid additive manufacturing. This is the classification by ASTM, where we go from one end, vat photopolymerization, to material jetting, to binder jetting, material extrusion, sheet lamination, powder bed fusion, and DED. Again, we would recall that this classification is not random, it's systematic, and it is based on the energy input. In vat photopolymerization, we typically have energies, say, in the order of milliwatts. A common laser example would be 40 milliwatt. And by the time we approach, say, powder bed fusion, lasers typically have powers of 500 watts. And in day-to-day, it is very common to encounter laser systems with powers of 3 to 10 kilowatt, 8 kilowatt or 10 kilowatt. For instance, for the hybrid additive manufacturing setup that we have here at IIT Bombay in our lab, it is equipped currently with a 3 kilowatt laser, but then we are in plans of enhancing that power further. However, it's very common to encounter other systems which come equipped with much higher power lasers. And among these, liquid-based AM processes are the two highlighted here, being vat photopolymerization and material jetting. A question can arise that in binder jetting also we are dispensing binder from this deposition head, print head or deposition head, and some binder drops coming out of here, which is again a liquid. Then why is this not classified uh, under liquid-based AM in the current scheme? The reason for that is we are talking about the raw feedstock here. That is, the material which you are printing has to be liquid in nature. In vat photopolymerization, the resin which is available in the vat is the build material. In material jetting, the material which we dispense from these nozzles is the build material. In binder jetting, however, as is clear from the schematic here, the built material powder is already available in the powder bed. What we're dispensing really is the binder. It serves a very useful purpose, whereas it binds the powder together, but it is by itself not the building material. Photopolymerization, as the name would suggest, is based on the principle of polymerization, where you have certain compounds which, under certain specific conditions, tend to form very long chains. And because of their long chain connected nature, they say exhibit certain unique properties. The photopolymerization based AM processes build object by photocurable liquid resin, which will cure or harden under the exposure to UV light. UV light scans the cross section of each slice to selectively cure it. Again, selective being the important word because we only want to cure the regions of interest. The entire vat or the entire printing area will be full of this build material at a time, out of which we only want to cure the regions which are relevant to our contours. After complete curing of a layer, the build platform goes up or down as the case may be, and the next layer of liquid resin spreads over or below the previous layer. This process is repeated for building the entire part, and the uncured liquid is drained from the vat and object proceeds for further processing. What is this further processing? So when we build parts by vat photopolymerization, They will also typically require, say, support structures for overhanging features, because in this case, the supporting material, which is liquid, uh, is not really as effective as support as in some powder-based processes. So we will need explicit supports. And since it is made of the same material, because we cannot have, say, two different sets of resins in the vat, they will mix or they will get, say, distributed uncontrollably. What we do is, and in some simple machines, even you might not have multiple lasers, so you need to print both the build region and the support region with the same laser at the same spot size, even same power, say. That is why what we do is we do not cure the polymer fully. We will cure it partially so that when your build is complete, you take it out. The part is it is solid, but it is still not very strong, and it will be somewhat flexible. You can bend it. If you try too hard, it will even break. The reason being that at this stage, we break off all the supports, then we put it into a UV chamber, where there is a floodlight of ultraviolet light of a wavelength relevant to the resin that you are using, and that part is left in that chamber for a suitable amount of time, and that is where the part gets fully cured, and then it becomes strong enough and it can be put to use. The schematic for photopolymerization is also shown here. You have this resin which consists of photoinitiators and monomers. Upon receiving suitable wavelength of radiation of suitable wavelength, the photoinitiators will get excited and turn into free radicals. These radicals will form chains with the monomers, and the chains will propagate to the extent till when these free radicals are available. Once the free radicals cannot be formed at a sustainable rate, the chains will terminate, leading to these long chain structures. The working principle of any, say, photopolymerization technology or machine can be broken down into certain subsystems. Some of them are listed here. First being the photopolymer liquid, second being the type and source of UV light, third being the scanning system, or how this UV light is being shined upon the resin material. Fourth is the build direction, because as we discussed, it can be up or down or maybe neither. And fifth is the recoating system, or how once a layer of resin is cured, how the next layer is brought into the system. So in terms of the scanning systems, we have several options, being galvanometer, flying liquid, flying optics, DLP, and mass. Galvanometer, in the simplest sense, consists of a pair of mirrors which are mounted to motors. And just like we would use a periscope in our childhood to view objects above our height, by controlling the reflection of light using two mirrors, galvanometer also works on a similar principle, except now the mirrors can also be actuated depending on your need. And we use the combination of these two mirrors to scan or shine the laser light all over the print area. Now the galvanometer mirrors are very light, and because of being light, they have very low inertia. So they can be scanned at very high speeds over the entire printing region and can be used to cover the region of interest. The flying liquid scanning system refers to a case where you are not scanning the laser or moving the laser per se, but you are scanning the moving the liquid vat itself. So say if your setup were such that the laser is fixed for some reason and you cannot move it, which is reasonable because laser optics are complicated and they are very costly to fix. What you do is you impart XY motion to your vat of liquid itself, while the laser remains fixed and just turns on or off depending on the need. A clear drawback of this as you can imagine, would be sloshing of the liquid around. That is, inertial effects will have a big part to play. Flying optics is the inverse case in which you fix your vat of material and you move the laser head, not just not just scan it over the surface. Of course, it is not advisable because then your entire laser optics is moving and they may get damaged if the speeds are very high. But then there might be a few limited applications for such a technology. Then again, we have digital light processing or DLP, where you have this small array of many micro mirrors, which is basically, say, the pixelation of a mirror surface into a large number of small mirrors, which can each be very selectively and very precisely actuated to shine light into a small region of interest. Again, depending on the size of each individual mirror and the number of mirrors into which you're dividing your overall large shining area, the resolution will be controlled. Then again, we have the mask, where instead of a discrete light, such as a laser, we are using a floodlight-like arrangement, which will scan or illuminate or cure an entire large area at once instead of doing it point by point. Sorry. Uh, yeah. And depending on the type of photoresist or photopolymer, whether it is a negative photopolymer or a positive photopolymer, the mask can be used to hide or expose the region which is of interest or the region which is not of interest. We also do an example problem on this type to further illustrate the point. Second subcategorization is based on the shape of the UV light, or more precisely, whether it is available in the form of a small beam of light, which you scan to very precisely control where which regions will be cured, or whether it is a floodlight. Now, a laser beam, of course, offers the advantage of precise control or precision of printing because again it's a very small beam. Typically, say its diameter will be or spot size will be some 40 micron or similar. So you can actually scan very fine features. But then on the other side, it will be comparatively slower. Not slow to scan because galvanometers can move at very high speeds. So it will scan very quickly. But then again, since you're doing or scanning a large region of interest, one point at a time, overall the amount of time taken will be longer. For some of us who are into R&D and who might have used an technique called EBSD, where again you scan an area but you do it line by line. You would be familiar with how long it takes. I mean, even with the most updated technology, depending on your detector type, even for areas as small as 100 by 100 microns, the scan type for a good enough resolution can easily run into a couple of hours. Floodlight, on the other hand, uh, say typically will be mounted on the back of your deposition head. So if this is the design of your deposition head, and at the bottom you have these nozzles from which you dispense liquid. The floodlight is often mounted just at the back of it, so that right after you dispense liquid here, and the deposition head has moved over some region, the UV rays will cure it. And it is not an instantaneous process, but it is a very quick process, and almost instantaneous. So you deposit, and in very quickly, the laser also cures it. The advantage will be, of course, being faster because it is illuminating a very large section, or in some cases, the entire print area at once. But then you lose out on accuracy and precision. And the reason for that being, as some of us would recollect from our study of photolithography, say if this is a cross section of your mask, this is the opaque region which I have hatched, and in the center is the region which you want printed or cured on your photoresist. The light in this case, as we said, is being shown all over because it is a floodlight. What we want is just this narrow column of light, which is very highly collimated and parallel, to illuminate and cure just this small region as we have specified. But in practice, this will rarely be the case. There will be diffraction of light, and a larger area will be cured than intended. And so we are losing out on accuracy. Next can be a subcategorization based on the shape of the liquid, whether it is available in a container in a volumetric fashion in the form of a vat, or whether it is being dispensed from nozzles as we just saw in the form of micro droplets. Uh, Ramamurthy, did you raise your hand? Do you have a question?
Yeah. So like what you told this floodlight, whether
Yes.
in DLP also is it possible to have a single scan that the entire curing can be done?
No, the technology of DLP itself is based on that array of mirrors. That is
Yeah.
where the name comes from, digital light processing.
Yes. Yes.
Yes. So that array of mirrors is key. Whether that uses laser beams or whether it uses floodlights, we'll be seeing in, I believe, the next lecture or next couple of lectures. Maybe that will be a good time to revisit this.
Okay. But it's not possible no, in with the DLP in single like
I don't see why not, because you can actually shine a floodlight on that array of mirrors and then selectively actuate only the mirrors with which you want to, say, illuminate the resin. But then again,
yes.
let us talk about this more when we reach that process. I think it'll be more helpful.
Okay.
Yes. The second case can be when you have the liquid getting dispensed in the form of tiny droplets from nozzles from a deposition head. And now comes the question of build direction. A typical example would be where the build direction is along positive Z. So say this is your vat of resin, and your part is being printed inside. It will be attached to some form of printing bed or plate. And once a layer is printed, this stage will move down so that more resin can come up on top of this deposited layer, and now this layer of resin can be cured by the laser beam. This is the most commonly encountered example, but this need not be the only configuration being used. What if we just invert this? And now instead of our stage moving down, it moves up. Z direction remains still the same. Now the build itself is proceeding along the negative Z direction. Of course, in this case, your source of illumination, whether a floodlight or a laser, has to be in the bottom, and this bottom face has to be transparent to this radiation. Are there any objective advantages to the negative Z direction as a build direction compared to the regular configuration? A few are obvious and come to mind. First is look at the amount of resin that you need in each case. In this case, if you're talking about the limiting value, for the negative Z build direction, we just need enough resin for equal to the height of one building layer. Whereas in the build with positive Z direction, our entire vat must be filled with resin. Again, if you have regions which may be susceptible to entrapment of liquid vat, say if my actual part geometry is something like this, which has some hollow section, if I'm printing it along the positive Z direction, these regions are all solid, and then I print this region with walls, but on top of it, I must print this solid region. And now there will be this section of or volume of resin which is entrapped inside. It will normally or automatically get evicted under the action of gravity in the case of the inverted configuration. But then you need not have any of these because we can just have a variable direction. As in, say you have a vat of liquid just like before, but now you have some flexible robotic arrangement which shines your laser light very close and in a very precise fashion in the laser, and this head itself moves. In which case you need not have a fixed build direction at all. Ramamurthy, you raised your hand.
Anyhow, uh, here the main difference between plus z direction and minus z direction. So with
Yes.
lesser amount of resin, we can complete the building of the part.
Yes.
Okay. Coming to variable direction, in what direction we are going to scan the part? It is variable only. Means always one direction or again in one part, whether it is possible to change the direction every time
Uh,
instantaneously.
have you encountered a five-axis CNC?
Yeah, I actually have not worked with that.
Okay, so the basic idea is that there might be parts where it is not possible or to machine or deposit in just one fixed direction, or it may not be the most optimal way to do it. Say if you have, just as an example, if you want to print uh, uh, impeller blade on some cylindrical base. So one way to do it is our regular. We print this cylinder layer by layer, and then when we come to these blades, we print it with some say supports or however. The other way is to do it cylindrically, where You have some cylindrical base with which you start. You deposit on top of it, and either your plate or your deposition head moves such that you deposit a layer here, then this turns. So either your cylinder can rotate or your head, which is say somewhere here, it can deposit here or it can move and deposit here and can come to this side and deposit on this side. So in this case, as you would see, there is no fixed direction of printing because either your substrate or your deposition head or both of them are constantly moving. We are not really sticking to a particular reference frame here, and that is why it's called like a variable direction print.
Okay, more flexibility will be there for that axis.
I Correct. That is why I asked if you are familiar with the 5-axis CNC because similar thing is used
Sir,
in 5-axis CNC for machining also.
sir, in lecture they told that robotic movement is a variable direction.
Correct. Yeah. So that is the what I schematic I drew you initially. If you have some type of flexible robot which can like go into the vat and shoot laser very precisely in a small region and then continue to cure and build. An example of variable printing direction is also in the video which I showed at the beginning. I think some of us were not there at the time. Let me just show it again. Um, okay, just a second. Let me bring it up. Oh, yes. So if we look at this example carefully, we will find that here again there is no single fixed direction of printing. As in some cases, the deposition head is moving vertically upwards or horizontally, or the part itself, as we can see, has some jagged shape. So this is another example of a variable direction printing and supportless also in this case.
So this support structure does not require for powder parts or wire also.
Typically, it may not be required for powders. Even in that case, we will encounter cases where it will be required. Definitely at the bottom of the part where it is connected to the build plate, where it acts as a machining allowance. And for certain complicated parts or large parts, you may still require support structures even in the middle of the part. But yeah, there are certain applications where the surrounding powder itself will act as a support structure, but not always. Ramana Murthy, you have a comment?
Actually, no, sir. It's automatically
Okay,
getting.
okay. It might be some
Is there any
lag.
difference in strength when the direction changes? Is
Yes.
there any difference in strength?
Okay, that's complicated. I mean, it's not a straightforward answer. There can be, yes, of course, because locally the dynamics of heat transfer uh, and the microstructural growth will of course vary. So it is expected that there will be a change in strength, but then again, strength, the way we characterize it, is a bulk property. What will be the bulk value? Will it be very different from a part which is printed along just one fixed direction? It's difficult to say. I think it will. I should not comment on it without carrying out any such experiments. But the microstructure will change I mean, I have seen some examples where it changed and microstructure dictates strength locally at least. So yeah, locally, of course, you will see a lot of variation. Say if you do a hardness mapping or elastic modulus mapping, you will see changes locally. But whether that will affect the bulk strength as a whole is a more complicated answer.
Okay, thank you.
Yes. Finally, the recoating systems, which are deep dipping, top feeding, and bottom feeding. Deep dipping can be studied well from this example of building along the positive Z build direction, where when your stage moves down, the surrounding resin will rush in and tend to accumulate over the built part. Because of the relatively higher viscosity of the resin, of course, this flow is very viscous and can also sometimes be slow. Then, something similar to a doctor's blade or a roller will come and it will be used to, say, spread a uniform layer of resin on top of the previously deposited part to be cured in the next layer. The next example can be of top feeding. One instance is of say micro droplets or small droplets of polymer, which can be dispensed by that nozzle array. And bottom feeding is the case encountered when we have a build direction along the negative z direction, where you want this resin to flow under the part from the sides and from the bottom. There are many considerations here. What should be the flow? How should the part move to allow this viscous resin to enter? These are things which we'll be discussing in the next week, I believe. And again, once you have or once you link these various types of subsystems, depending on the choices which you make, you can actually end up with various technologies which are commercialized. For instance, if you use a galvanometer type of scanning system, the shape of the UV light is in the form of laser. You're using a liquid vat, building along the plus direction, and doing top fitting. You end up with 3D systems SLA Zephyr, which is an improvement over 3D systems original SLA, which was the first 3D printing technology. The only difference being now from deep dipping, we have switched to a top feeding mechanism. And there are many others. For instance, if you are using a DLP type mirror array, using a floodlight, and then using a liquid vat, building along the negative z direction or building moving a stage up with every step, and using bottom feeding, because for negative z direction you have to bottom feed, there is no other way. You actually end up with Perfectris Achilles. And similarly, there are a lot of other systems. In fact, vat photopolymerization is one of the most well explored 3D printing technology, and so a large number of commercial systems are available. Um, so we have discussed the lecture contents for this week and also looked at a few illustrative videos. Let us just take a short break, and when we resume, we'll be solving a few example problems which will help you solve the assignments for this week. So see you in around 5-6 minutes.
Excuse me, sir, I have a doubt. Sir, am I audible?
Okay, so it's a problem solving tale. The first question here deals with uh, grid cutting. Uh, we are told that a rectangular and a square contours of given dimensions are to be fabricated using the laminated object manufacturing process from a given square sheet. And we're asked to find the ratio of uh, the unwanted material U for the square and the rectangle. So as we just saw, the given sheet is a rectangular sheet of dimension 10 centimeter by 10 centimeters. And we have to cut out from it rectangular and square contours. The rectangular contour being uh, 8 by 3, and in the second case, a square contour which is 5 by 5. And since this is a grid cutting operation, we'll be focusing on removing the unwanted area, and we are asked to find the sorry, the area of the unwanted material for the square and the rectangle. So let us first find them. So in this case, the print area or area to be printed is
Sir, unwanted
uh, sorry Dinesh, could you just unmute again?
unwanted area 50 and ratio is 1.04.
Thank you. Let me also work it out for the others, but thank you for the answer. So printed area is just 25 centimeters square. Total area, as we know, is just 10 into 10 centimeters square, which is 100. And thus, the unwanted area is total minus print area, which is 75 centimeters square. We repeat this exercise for the rectangular region, where the print area is 8 cross 3. Yeah, 8 cross 3, which is 24 centimeters square. Total area is 10 cross 10, 100. And unwanted area is simply total minus print, is 76 centimeters square. We have to find the ratio of these areas for the square to the rectangle. So which, as Dinesh pointed out, is close to 1 point something. I'll just calculate the exact value. Sorry, slightly less than 1, or 0.98. The second question is related to infill density. and says that we have a cube of given dimensions and a cuboid of given dimensions with different infill densities. Both are fabricated using the FDM process. We're asked to find the ratio of the volumes of infill material used. So somewhat similar to the previous case, but just let us work it out. So for the cube, we have the nominal, sorry, we have the nominal something, no, we have the something is up with my pencil, I'm not sure what. Yes. What did I open? Some old yeah, sorry. So we have the nominal volume, which is equal to the design volume, which is 20 cross 20 cross 20 centimeter cube. And we have the infill density of 40%. What this means is 60% of the volume inside this finely built cube will be empty or void. Only 40% of the region will be occupied by actual build material. So it has to find the volume of infill material. Therefore, volume of infill material for cube is 40% of 20 cross 20 cross 20, which will be about 8,000 centimeter cube, or this is 4 into 800, 3,200 centimeter cube of material. We repeat the same exercise for the cuboid, in which case the nominal volume is 5 into 10 into 20. The infill density in this case is 60%. And so the volume of infill material actually used is 60% of 50 into 10,000 centimeter cube, which is simply 600 centimeter cube. Now again we just find the ratios for cube to cuboid. So say volume of infill material for the cube by that of the cuboid is 3,200 centimeter cube by 600 centimeter cube, which is just 32 by 6, or 16 by 3, which is 5.33. The next question is asking us, what will be the difference in toolpath strategy for exterior contours obtained from direct slicing and indirect slicing? We looked at direct and indirect slicing last week, but just to recall, direct slicing was one where we started with the exact CAD model. Sliced it in this example using planar layers, and then we looked at any given layer, say this is the nth layer, where the intersection of the exact CAD geometry and the slicing plane gave us the contour. In the case of indirect slicing, again we did start with an exact CAD model, but there was this intermediate step where we approximated it using an STL file. We tessellated the surface with triangles, uh, lost out on some of the geometrical features such as the curvature region, but then had a approximation which is easier to handle and lighter. Now, when we slice this, look at say the nth layer. Because of the intersection of this slicing plane with the approximated geometry in the form of STL file, now the contour is in a shape of a polygon, as in it consists of several straight lines joined together in a loop and they have vertices. In the previous case, the contour was actually a perfect circle. And so the difference in the two cases, yeah, if I might just write it descriptively, is say in direct slicing. We found the intersection points where the slicing plane intersected with the exact geometry of the CAD, and then we joined these intersection points together or interpolated between them using some high order functions. To obtain the final contours with a very high amount of accuracy. What are such high order functions? A very simple example can be that of polynomials. But you can come up with any other. Whereas in the case of indirect slicing, which is the more commonly used of the two, and which we also encounter in our common CAPP software, the intersection of the slicing planes the intersection of the slicing planes with the tessellated triangles gives us the intersection points, which in this case we interpolate using just linear segments or line segments. Which makes for easier handling and storage, but then loses out on some of the high accuracy features, and we join these together to form the contours. So the difference lies in that approximation. In one case, we use a high order function for interpolation, whereas in the other case, we work with linear segments. Okay. The next question asks, find the odd one out in the context of area filling methods for toolpath planning. Option A is laminated object manufacturing, B is stereolithography or SLA, C is binder jetting, and D is DED or direct energy deposition. Please notice that these processes are very different in many different terms, say in energy consumption, in the type of feedstock used, in the size of the parts that they can build. But we are asked specifically to find the odd one out in the context of area filling methods. And it might be obvious here because of all the methods that we discussed, in most of them we were focused on filling the region which was our region of interest or the region in which the part was to be built. But there was this one process where, if I'll just briefly draw the schematic again, if this was the printable region for a pass and this is the region which you want to deposit, there was this one process in which we were focused more on what happens on the outside here. So on how to get rid of this extra material per pass, and on filling the infill region itself. And that was the process of laminated object manufacturing. The reason being that this sheet, which is the say feedstock for this process, already contains material here. The material is already present. We do not have to add any material here per se. We just have to separate this region or any other, say, even if there are any interior contours, then we have to machine this one out as well. But essentially, we have to separate this from the existing sheet. And that is why we are more focused on how to cut it out. First via some very precise cuts with controlled or fine laser size, laser spot size, and later using coarser laser spot size or higher speeds without caring so much for accuracy. We just want to cut out the remaining material so that later it is very easy to remove. Whereas for all the processes such as SLA or binder jetting or DD, we are more focused, or we focus our efforts into depositing material in the regions where we want to print the part. So in the specific context of area filling methods, laminated object manufacturing is the odd one out. Question 5 is asking us, on the basis of sensitivity to UV energy source, what is the type of photopolymer material generally used in liquid AM process, whether it is the positive photoresist type or the negative photoresist type? And for this, we will just very briefly revisit this concept of photolithography, which some of us might have studied, where we start from a substrate, and in the first step, we apply a layer of photoresist material on top, which is given in blue here, this one right here. In the next step, we have some mask which has opaque regions, such as the ones I'm hatching right now. And there are a few openings through which light is allowed to selectively pass. Now, the regions from which the light passes, below them, the light interacts, or the incident radiation interacts with the photoresist, and you see that in this grayed out region here. The one I'm currently hatching with green. This is the region of interaction of the photoresist with the incident radiation. Then we apply the developer, which is a chemical machining step. And then depending on the type of photoresist, either the region which interacted with the radiation will survive and the rest of the material will wash off, which is the case of a negative photoresist, or the region which interacted with the radiation will get washed away with the developer and the rest of the photoresist will survive, which is the case of the positive photoresist. In the case of using a mask in a liquid type AM process, what we saw is that we expose the region of interest to energy radiation and the region of interest survives. As in from the example that we saw, say if this is the printable region for a certain layer and this is the contour which you want to print, then the contour region will also be the region which we expose to light by using the mask. This is the region which interacts with the incident UV radiation. And in the next layer, or finally when the build is complete, this is also the region which will survive. All of this surrounding resin will get removed. And so since the region which interacted with the UV radiation survived, the nature of the photopolymer in this case is similar to that of or analogous to a negative photoresist. The sixth question says, during deposition of material in a single layer, there are certain steps at which the process becomes unstable. Which of the following may be called as such unstable steps? Is it during the start of the print? Is it when turning a corner in the toolpath? Is it at the stop of a print? Or is it in the change of Z height of the deposition head or build platform? Let us examine each of these points one by one. The first one is saying start of print. So, as most of us would have encountered during our uh, workshop practice or welding demonstration, when we start to deposit a bead, during the start of deposition and during the end of deposition, there is this slight bulge. There might also be certain processes where uh, at the start of deposition there is under deposition, but mostly this region in the middle is steady state and has pretty uniform characteristics. Irrespective of whether it is under deposition or over, we can definitely say that the start of the print is a time of instability where the process is not really under our control, is rather unstable. Turning a corner in a toolpath. This can be very easily illustrated with an example. If we try to build a cube, which is one of the first test objects that one prints with a 3D printer, we'll find that we'll never have these very sharp edges or very sharp corners. Instead, what we have is something like this. That is, these corners become rounded. And the reason for this is because in two dimensional CPC, we are coming along one direction and then turning at 90 degrees and then going in some other direction. If we do this at constant speed, because of the change in direction, there is still some acceleration. Or deceleration, as the case may be. And because of this acceleration, the process becomes unstable. There has been some research into how to deposit these corners well. And while perfection is very difficult to achieve, something which can be done is if we enter the corner slowly and exit fast. Of course, the amount of material deposition or the feed rate also has to be modulated carefully in conjunction with the speed so as to achieve uniform deposition characteristics. But then turning a corner in the toolpath is also a time when the process is unstable. And similar to the logic for starting of print, the time of stop of print is also unstable because your machine head was moving at some finite velocity and then suddenly it has to come to a stop. Of course, it's not instantaneous and it decelerates over some small, very small distance. But even then, because of this sudden deceleration and inertial effects, there is over deposition or in some cases under deposition at the stop of print as well. So this is also a time of instability. The next question is asking us, what are the advantages of bottom feeding method in vat photopolymerization? This is something we already discussed during the lecture. So we saw that in the case of bottom feeding, less resin is required and the critical amount of resin is just equal to the height of a single build layer. Does the bottom feeding method offer better accuracy and finish? That is not a general statement because as we know, the accuracy and finish will always depend on the process, machine and material combination. Just the use of a different feeding method need not by itself guarantee a better accuracy or better finish. But are there less chances of entrapment of uncured resin? Yes, that is so, and it is because of gravitational effects. If there are any hollow sections in our print, in the inverted configuration which uses bottom feeding, because of the effects of gravity, um, any liquid resin material will flow out by itself, whereas there is a chance that it can get entrapped if we are using a top feeding or a deep dipping type of feeding mechanism. So A and C are the correct answers. How can existing CAM packages be used for area filling of a freeform 3D surface? This is something we did talk about a little during the lecture, and the way we go about it is in some of our labs you might have seen that a welding gun is simply retrofitted to an existing CNC machine. And perhaps those of us who have encountered or worked with 3D printing know that we use the same G code or similar G code packages which we use for machining. The only difference is that now there are some additional commands for start of print, end of print, say arming of the laser head, retraction of wire for checking of contact errors and others. But the motion of the deposition head is still controlled by the same CNC commands which are used for machining. And thus, there is a very, say, great potential of existing CAM packages to be adapted for filling of free-form 3D surfaces or 3D printing. These were originally used for, say, machining. So we just extract the machining strategy, which will basically give us the G code for motion of the deposition head. This, as I said, will modify, adapt, and even add to as necessary. And what will this allow us to do is instead of removal of material, which was its original intent, we will now repurpose it for addition of material. And this is how we can adapt existing CAM packages for area filling of freeform 3D surfaces. How are the individual mirrors of a DLP system manipulated? Um, since we have not discussed the technique yet, it might be better addressed in the next week. We also have schematic of DLP mirrors, which I was talking about, but then again, we'll discuss it more in the upcoming week. And the 10th question is, what are the disadvantages of a galvanometer-based liquid AM process? Again, I just very briefly described what a galvanometer is. I said that it consists of a pair of mirrors which are attached to motors and can rotate very quickly, are very light and thus have very low inertia, and can thus scan the entire print region with laser very quickly. But what are its disadvantages? Is it low scanning speed, high production time, low accuracy, or change in beam shape away from the optical axis? Let us examine these one by one. I mentioned that because of the very low inertia of the mirrors and the high speed with which the motors can turn, the scanning speeds can be very high. That need not translate into very fast print times because for printing, the laser still needs to interact with the material for a finite amount of time, and if you are doing it point by point, it can, in sum total, take a long amount of time. However, the scanning speed is still very high, and thus this is not the correct answer. Are high production times a potential disadvantage? Compared to floodlight like lighting systems, yes, because as I said, this in galvanometer based systems or processes, the laser interacts with the resin material point by point and thus can lead to higher production times. However, because of this point of by point interaction and the very fine size of the laser beam, the accuracy is high. However, very close to the optical axis, uh, the beam retains its circular shape, but away it leads to an error called astigmatism or stigmation error. And this there can be errors and change in beam shape away from the optical axis. Both B and D are correct, but what stigmation is and what type of error it can lead to, we'll discuss in the upcoming week. This was it for week 3 of the live sessions for the fundamentals of additive manufacturing technologies. Thank you for tuning in, and I hope to see you again next week. Thank you.